Okay, so what we did last time is we had talked about rate laws, all right, and we had decided, we had come up with an equation to help us figure out what the rate of reaction was. And we got to the end of the class on it, and I'd forgotten how to do exponents. And Noah helped me with that after class. So let's go ahead and do a problem and use it, okay? So what we've got is we've got a problem here from the back of your book. What it's going to require us to do is we're going to try to figure out what the rate law is for this reaction. And I want to remind you that the equation we use is rate of 1 over the rate of conditions 2 is going to be equal to our concentration. I'm just going to put A in here, okay? Concentration under condition 1 over concentration under condition 2 raised to some power. Well, that power is usually going to be 1, 2, or, well, 0, 1, or 2. Although we had a problem last time where it was actually 0.5, all right? And there are complicated things that can happen that can cause that to be the case. And we'll get more into the detail of that in Friday or maybe on Monday, okay, in terms of the mechanisms of the internal workings of reactions. So far, we've just looked at a reaction like this, and we said those are the reactants that are going to show up in the rate law, well, maybe or maybe not. And so it's not exactly the sort of thing of how something might be written. So let's look at this reaction here. Our rate law, what is our rate law without knowing the exponents? So we'll just put in variables for the exponents. What's our rate law for this going to look like? It's going to be rate is equal to what? K, some constant K, times the concentration of, this thing on the left there is T-butyl alcohol. You don't need to know that until next year at least. Okay, the concentration of that, what else do I need to put in here? Concentration of HI, right? Hydroiodic acid. That's what I would call it, but HI. Okay, and this is raised to some constant, and this is raised to some constant. Okay, some power, telling us the order. So there's some order for this, and there's some order for that. Let's go down here. So we're going to solve for those. Let's go down and look at this. You can solve by inspection. You can also calculate it. And we're going to do both of those here. Let's take our hydroiodic acid first. So I've got 3 things here, right? If I just want to look at one of them, what I can do is hold another one of them constant. So if we look at our concentrations here, for these first 2 conditions, which one's being held constant here and which one's being varied? Which one's being varied? It's easier to say. HI, right? The HI, hydroiodic acid. But the HI is being varied, so these aren't going to affect the rate at all because they're not changing. So by inspection, though, I double the amount of HI, and what happens to my rate? It goes up some tiny, tiny amount that's probably just in the error of my measurement. We're going to say those are the same, right? Less than 1% difference there. And so we have barely any change there. So so the concentration of HI does not affect my rate of reaction, right? Essentially, what order is it then? It's 0 order, right? So if I put a 0 in for N up here, make that 0. Something raised to 0 is what? 1. So that becomes 1, and it's going to go away, right? Okay, so we don't need to worry about that. Now let's solve the next part of it. And you might be able to look at where the concentrations of the T-butyl alcohol are changing here, and by inspection figure out what that number is. But let's use the equation to solve it anyway. All right, so I've got the rate of one over the rate of the other. So if we look at here, I'm going to take the rate. So I'm now using this bit. And so the rate of 1 is going to be 0. Actually, let me write the equation out again so we're looking at it. So remember, the equation is the rate of 1 over the rate of 2, and that's going to be equal to the concentration of A, whatever A is, over the concentration of A, where this top A is under the goes with the rate 1, and this bottom A goes with the rate 2. All right, that's not a concentration bracket. It is a parenthesis raised to some power. Okay, and in fact, actually, I'm going to make this power an m, because for what we're doing right here, it's going to be this m, right? Could be whatever letter. So let's go ahead and put those numbers in. So now I have my rate 1, which I'm going to take the top one for that, is going to be 0.806 molar per second. And then my rate 2 is going to be 0.403 molar per second. And my concentration one, the one that goes with the top rate, is going to be 0.200 molar. And my bottom rate is going to be 0.100 molar to the m. If I take this first one, let's take the left-hand side of the equation. What if I divide 0.403 into 0.86, or 0.806? I get 2, right? You guys see that? So this becomes 2 is equal to, what is in the parentheses? 0.2 divided by 0.1, what do I get? I get 2 to the m. Okay, so what's m going to be? 1. You can see that, but let's say it was more complicated, like that 0.5 we had at the end of last lecture. Then the way to solve this is you use logs. Remember, logs are your friends. They're a little bit complicated, and sometimes friends are like that. But what I can do is I can take the natural logarithm of both sides, or I could take the regular log and make this work. I could take any log. But ln of 2 is equal to the ln of 2 to the m. Okay, and what's my log property for exponents? If I have something, logarithm of something to the exponent, what can I do to that exponent? I can pull it out front, right? Okay. So an interesting thing is when you take a log of things that were multiplied, you can add them, and when you take a log of things that are up to an exponent, you multiply them. And so m logarithm 2, right? That's what that becomes. And now it's pretty obvious, right? I could divide, this is a times here. Now that I've got a times, I can actually divide both sides by the logarithm of 2. And what I end up with is this is 1, obviously, is equal to m. Yes?
This is probably a stupid question. But
It is not.
If the numbers were different, do the LNs cancel, or do you have to put that into your calculator?
So let's say the numbers were different, the LNs didn't cancel.
Yeah.
I would just take the logarithm of those numbers.
And then divide them.
And then I would divide them.
Okay.
Yeah. And we'll do something where we have to use logarithms a little bit later, for example, in the class. And so we'll get some practice with taking the natural logarithm of things. And if anybody's having problems with that with your calculator, please call me over when we get to that. Other questions? All right, let's go on then. We're going to talk now about the integrated rate laws. That's what most of today is going to be about. Okay, and when we say integrated, we mean integral, like from calculus. Okay, so those of you that are calculus should hopefully recognize what's going on here. If you haven't had calculus, we just have a set of equations you need to worry about. Okay, we'll just use the final equations. So these are the equations we care about for this class. All right, how we get to those equations, once again, for those of you with calculus, and I'm going to stop talking about calculus pretty soon here, but we did these, right, from deriving these. in terms of the order. So if you take that, you can do calculus to them, all right? So we can take, what this says is I have a very small change in time associated with a very small change in concentration. And then I can take something called an interval and I get this. If you've had calculus and you want to talk about how we got there, we can do that after class. But otherwise, you just need to know these equations that are in the yellow. All right. The important thing about this, though, we love to do this in chemistry, is that all of these equations are equations of straight lines. This is equal to y is equal to mx. Whoops. Mx plus b, right? See that? That's the form of that equation. This equation is y is equal to mx plus b. This equation, same format, y is equal to mx plus b. So the only difference between these equations is what I plot. We saw this before when we did the Clausius-Clapeyron equation, that we could actually put it into an equation that would give, or a form that would give us a straight line, and so we could plot things and determine things from that. Now, I'm not going to have you hand plot in the class, or I'm not going to have you hand plot for a test, a quiz or test. Okay, take too long. But what we do have here is I could give you a set of plots and ask you what order something is. All right, so let's go ahead and look at what order, how we would do this. And you may need to be doing this for your lab report. I know you're doing kinetics this week. So I have graphs here. This is an equation for a straight line here. What do I plot? If I want to get a straight line, what do I plot on my y and x axis for this one? If that's our zero order plot. T on the x-axis and concentration of A on the y. So you see I'm taking that and that. I'm taking my y and my x. Okay? How about somebody else? How about on the next one? How about, so this is zero order. This is first order. How about the next one? Still T on the x-axis. And then the natural logarithm of A over here. Okay? And then what would I plot finally on my second order plot? One over a concentration of A is my y, and my x is still T. Okay? Does that make sense? So these are going to give me straight lines if the actual order of the reactive tips. What will the straight line look like for this one? It's straight and it has a negative slope, right? Because I've got a negative in front of the K. So it's going to look like this. And what is the value of that going to be? It's a y-intercept. Hang on. It's my starting concentration of A, which intuitively makes sense, right? If this is my time zero, that's how much A I had when I started with it. Okay? And that's what's going on in this law. I don't know that I identified it from last time, but this is our starting concentration of A, and that's whatever concentration of A we have at that time. Okay? Same thing here. That's my starting concentration of A, and I take the natural logarithm and I get the natural logarithm of what A is at any given time. Okay, that's what we're going to use these for, figuring out how much reactant I have at a given time. First order. What's that line going to look like? It's straight and negative slope again. So we go like that. And what is this one going to be? What's the value there? The natural logarithm of A naught. Okay? And then finally, what's the other one, the last one, second order? Now we get a nice positive slope. All right, and we're going to have A 1 over A naught is there. Excuse me, questions? Okay. So let's go ahead then and let's try a problem using this stuff. All right. We're not going to do the plots yet, but we can use those equations. Yes.
So you said that we'd have to be able to differentiate the graphs from like which order it would be. How would you do that for the first and the second, or the zero order?
How would I make the graph? How would I ask the question?
Yeah, like would you ask us how, like which one is which?
I would ask you whether, so what I would do is I would maybe give you some graphs and I would say, what order is this order is this reactant? Okay, so if I get you to hold off for a bit,
Okay.
I'm gonna graph this. I'm gonna make you suffer through me graphing this in real time. But it's something you're gonna want to do for your lab reports, I expect. So we'll get to that. We'll get to a problem where we can do that. Just real quick on the lab reports. Are you supposed to figure out the order of the reaction of some reactant this week?
But you do it with math.
You do it with math, not with a graph?
The integrated rate law.
Oh, okay.
Just do it with math.
You have to make a graph later
You
on.
do have to make a graph, but you figure it out well before.
And then you graph it with the correct rate law?
I think so.
Okay. So you'll get to see kind of how we would graph it. It's not exactly like what this problem at the end is going to be. But we're not doing that yet. All right. So here, this is an example of a problem where you would use the integrated rate laws to solve for one of the things. And this is like many of the problems in this class where what we're given is we're given an equation that has a whole bunch of variables in it. We're given all of the values of all the variables except for one, or a way to calculate all except for one, and then we have to solve for that one. All right, we've seen that over and over again. So zero order. What this question is asking, a reaction begins with, that's my A naught, a concentration of Y equal to 0.350 molar. For each given situation, find the amount of time required to reach a concentration of 0.2 molar. That's my A. All right. So this first problem is saying do it for a zero order rate law. I'm just going to write down the zero order rate law here. So that's going to be A, right? That's the one that has, it's the easiest one perhaps, is equal to negative K times time plus A naught, right? That is my zero order rate law. Where did I get it from? I got it from here. Let me erase the red stuff over it. It's the green one, okay? And this problem is asking me for zero order. So you'll be given these equations, they'll be at the top of your tests. But let's go ahead and solve for this then. So A is what we're trying to get. That's what, after some amount of time, we've got the concentration of A is that. So I'm going to go ahead and put 0.2, whoops, and to 0. 0.200 molar is equal to negative K. I'm given K, right? K is 5.2 molar. This is going to be a fast reaction. 5.22 molar per second. That's a lot of molar per second. Times whatever time I'm solving for that, plus 3.5 is what I start with. That's A naught, 0.350 molar. Okay, so now I've got everything except for T, and I need to solve for T. I'm going to go ahead and I'm going to subtract 0.350 molar from each side. Sorry, 0.350 molar. And that's going to give me what? Negative 0.15. 0.150 molar. Yeah? You guys can check that out me. Is equal to negative 520 molar per second times time. I've got molar on this side, molar on that side, so I'll just go ahead and cancel them. It's going to give me time in seconds. I can see that coming, so I'm happy because seconds is a unit of time, right? And so now I just need to divide both sides by negative 5.201 over seconds. All right, over on this left-hand side, I've got 1 over seconds. I've got seconds on the bottom, which is the same as seconds on the top. All right, these go away, negatives go away. I remember this is a really small number. It's like 0.002 something. So 0.02, let's see. I'm just going to match my significant figures above. I had 3 significant figures, so I'm just going to go ahead and use them. I subtracted, yeah, I still had 3 significant figures. Okay? Does that make sense, what I did there? All right, I want you to do B. All right, so do B. I'm going to go ahead, I'm going to scoot this up so we can see the numbers, and I'm going to write out the first order rate law here for you. This is the fancy one with the logarithms, the natural logarithms in it, and that's equal to negative k times t plus the natural logarithm of a start. All right, go ahead, let's take a few minutes and have you actually solve that one. We have a super slow rate constant this time. Tiny little number. And if you've done B, you can go ahead and do C for practice. Please ask me to, a number of people wanted help with B in the first hour. Please ask me to come over if you have questions. Want to know where your logarithms, how to do logarithms.
Yeah, it's because the rate is really, really big, or the constant
18,
is really small.
18,000.
Yeah. And then C is normal again.
What was that?
And then C is normal-ish.
Oh, in terms of size of, yeah, I mean, they're just moving the numbers around, so. And these are uncatalyzed. They're probably uncatalyzed reactions. We haven't talked about catalysis yet, so they could be really slow.
Gotcha.
Yes, 10 to the negative 5.
Why for the integrated rate law or second order, why is K positive?
Yeah, because the calculus. Have you had calculus?
Yeah, I took Calc 2 last semester.
Okay, so you take the, you want to go ahead, somebody else is asking questions. Write out the law before calculus.
What is it?
Yeah, it's, what is it? It's delta A over delta T is equal to,
Oh, I know what
it's second order, so K times A squared, right?
K squared, and then you just take the integral of those sides, right?
Well, we need to actually change it so it's a dt, so it ends up being, right, we're going to divide this side by A, we divide A over here, so we have dA over A, and then we multiply T times both sides, that makes sense. So that it becomes D concentration A over A squared. Oh, that was
Oh, because you have to have your variables all on one side.
right.
That makes sense. Okay.
And then you'll take integrals.
K times delta T. And
Then
then,
it's dt, not delta. It's calculus.
oh, right. And then.
Delta means it could be any change. dt means it's an infinitesimal.
Gotcha.
Are you gonna do good, or do you
Yeah,
want-
no, that makes sense now.
And so if you pick it up a power, and then pick up the power over power,
Got it.
you might have a better way to do it. That's a great question. So, well, I got a good question here. What's the estimate item 1? It means 1 over s. Same thing, 2, because the exponent is negative. Okay, let's go ahead and work this one together. There it is. Okay, so if we look at this, let's first answer. Let me show that answer though, or talk about that unit thing. So we've got s to the minus 1. That is the same as that's the exponent, so it's 1 that's the same as 1s, like that. If I had s to the minus 2, which I don't know if we're going to get in chemistry, but that would be 1 over s squared. Does that make sense? How we think about those. So often we'll abbreviate something that's on the bottom that way. Same sort of thing with this molar to the minus 1. Okay. Let's go ahead and put our numbers in. I think at this point I know most of them. It was what, 3.1 times 10 to the negative 5th. So I've got a logarithm, natural logarithm of A concentration. My concentration, this is the final concentration, which was 0.200 molar, right? That's equal to negative K, which was 3.1 times 10 to the negative 5th, right? And then that's 1 over seconds. I'll write it out like that, times my time, which is what I am solving for, plus the natural logarithm of A naught, which is the starting amount of A, which up in our problem was 3.50 molar. All right. Now, easiest way to solve this at this point is I can't cancel those ln's. I can't pull one over and divide or anything. I'm just going to convert them to numbers that aren't logarithms. So if I take, I'm going to take the natural logarithm of 0.2, and I get negative 1.61 over here. Then that's on the other side, I've got 3.1 times 10 to the negative 5th, 1 over seconds times temperature, plus the natural logarithm of 3.5. Okay, and that's going to give me negative 1.05 is over there. All right, so now that they're regular numbers as opposed to logarithms of numbers, right? Since they didn't match it, there wasn't an easy cancel there. I'm going to add 1.05 to each side. All right, if I do that, I'm going to end up on this side with, this ends up being negative 0.56, I think. Yeah? Correct me if I did that in my head. Correct me if I made a mistake there. And 1 over seconds times time. All right, and so now I would just divide, now I'm going to divide both sides by 3.1 times 10 to the negative 5. One over seconds as well. I'll bring my units with me. And then so those cancel, this all cancels. Over here in terms of units, I'm going to have seconds on the bottom, which is the same as having seconds on the top. Okay. And so what have I got? 0.56 divided by 3.1. I get a fifth, and I get 18,100. Seconds is what my time is equal to. All right. Somebody pointed out to me last time that significant figures wasn't right because I actually did. Officially with significant figures, as you go through, every time you switch from multiplication to subtraction, you need to actually do your rounding. Otherwise, you shouldn't do your rounding as you go along. So this really, for correct significant figures, is that. But I'm pretty lazy with significant figures, although I do care if you're way off. And so I would just take everything, I just take the number that are in the lowest number of things that's in the problem, and I carry those on. Okay, yes?
So on M, when it comes to the natural logarithm,
yes.
the M cancel out.
Where it comes to the natural logarithm, what were you saying?
So you know how you got the natural logarithm of 0.200 M?
Yes.
But then,
The molar, yes.
yeah.
Just the molar just goes away.
Okay.
So logarithm, it's a little complicated. Just don't worry about it. In the end, okay, so we know time has to be, a way we can fix that in our heads, at least in thinking about the answers, time has to be just seconds, minutes, hours, years. It can't be molar per second because it's time. Does that make sense? But yes, that's a great point there. What happened to my M's?
Now we just gotta figure out, like,
I-
why is it second?
I can't, because you're subtracting it, it's not going away really. So you just have to say it's okay. Bye-bye. Does that make sense? It does make sense maybe, but in terms of why, but I'm going to hand wave it away. Other questions? Okay. All right, well then let's go ahead and do an example of how we might graph this using the integrated rate law. Actually, before I do that, I want to talk about something that's a concept we've already used. Okay, when we want to figure out the rate of one reactant, we have multiple reactants going on, right? We had our HI example up here. Okay, well, not this one. We had this one. We had two things going on, and so what we had to do is we had to say, well, that one's constant and these are varying, so I'm just going to look at these. This one doesn't matter. And then that one's this one's constant and this is varying, so I can look at that to figure out the rate law. All right? That is called pseudo first order kinetics. I just realized last lecture that it's a little bit weird calling it pseudo first order kinetics because your thing might not be first order, okay? But by holding something constant, you can just be looking at the kinetics or the order of the other thing, the thing you're varying. Does that make sense? So pseudo first order kinetics. It involves holding everything, concentrations of all reactants constant and varying one. Okay, and so this is how you're going to isolate the order of that varied reactant. So I'm a biochemist, and I use pseudo first order kinetics all the time, and it's never bothered me that it was called pseudo first order kinetics, because in biochemistry almost all the time, you have an enzyme and it takes two things and it uses them together. It's almost always two things. I've got A and I've got B and I bring them together and I make something new. Okay, does that make sense? So all the enzyme stuff is about that. So then you hold in kinetics, in kinetics I used to do in research, I'd hold everything else constant. I'd hold the other reactant. If I had two reactants, I'd hold one constant, and actually at a high value, so it wasn't changing, so it essentially didn't change over the reaction. And then I'd look at the other one. So that's what this refers to if you hear that. All right, so this problem actually is kind of like that. Look, this problem's vague about, we don't even know what the reaction is. It's iodine as a reactant in a certain chemical reaction. All right, well, might be iodine's reacting all by itself, but it's probably reacting with something, okay? But it's a chemist measured, but they're not going to tell us the reaction. A chemist measures iodine as a function of time as shown below. Use this data to graph it as zero order, first order, or second order versus time, and based on these graphs, figure out what the order is. All right, so what am I going to be looking for in those graphs? I'm going to graph it three ways, and whether I get a straight line. Okay? The one that gives me a straight line tells me which order it is. And so this is something that you might need to do for lab.